Excellent. Very good. So today, today we will continue to talk about the important concepts, the bin element, okay, bar element. So before that, let's go through some updates of the logistics so that all of us are on the same page. So can you guys see my shared screen? Can you hear me? Yeah, okay, Corey, very good, very good. Sean, okay, good. Okay, so let me change to the laser point. You guys still like the red color, right? Red color, okay. So I will keep this color. Let me know if you want to change to other color, okay? We have a blue and green options, okay? Excellent. So as we said, homework 0 and homework 1 are used for you to practice, and you use that to prepare your quiz and exam, midterm exam number 1, right? So as you can see, everything goes like what I introduced to you. Homeworks are most comprehensive. Quiz will be simple, but very sharp to the point, to the key concepts you need to master. And then the exam will be simpler than the homework, but more sophisticated than quiz. So I hope you all of you have used those opportunities to practice, to strengthen your understanding. So far, based on what I saw from TA's grading, you guys all did excellent. You guys all did outstanding work in the exam and the quiz. So that's great. So we will keep our teaching pace, and I hope you can learn as much as possible in the class, okay, and continue to do great job in the coming exam, okay. We will post the homework number 2 very quickly after we finish some materials, and the homework number 2 we will have the deadline to submit. Then you will submit your solutions. But the homework number 2, those you can do together with the classmates. If you form a group, that's fine. But each member, each of you submit your own solutions. Okay, you can do individual as well. That's fine. But the point is, you use those homeworks to practice and then to learn, strengthen your understanding. That's the key. Okay. We'll have the exam number 2 coming. That it will be on October 19th. It will cover all the materials we would cover before this date, okay? Especially the new materials. So in the homework in the exam number 1, some of you told me that question numbers, problem numbers might be too much. The time is not enough because it's class time, right? 50 minutes. So the time is not enough for you to finish all the homework number 1 problems, even you know how to solve them. So that's great feedback. Don't worry about it. We have two things to help you. Firstly, in the exam, we care about how you solve the problem, the logical process. You just lay out the steps you are doing. We don't care too much about the final quantity, final results. Okay, so just show you can do it and show it correctly. That'd be great. And then from the exam number 2 on, we will reduce the problem number so that will be sufficient for you to finish within the class time. Okay, so no worry at all. So it will be on October 19th, Wednesday. Okay, so we will use the same procedure as we did for exam number 1, and it will be on the class. Okay, and I hope all of you have completed the EPICS tutorial video watching now. So we have uploaded 3, and we are going to delete them now. So please keep a copy for yourself. And we in this time, end of October and beginning November, we will you will watch the rest of 2 videos during the class time, and we will not meet in the class in the Zoom. Okay, so follow the same way. And before that, we will also post the project we only have one project, that is Abacus project. You can use Abacus to solve that, okay? And I have emailed you the link where to download, where to access Abacus. So follow that. We only have, at each time, at one time, we have only 20 students are able to access Abacus online. So make sure that after you finish, log yourself off, and then other students can jump in to use, okay? So we did it many times in the past semesters. It went very smoothly. So students are all coordinated very well. So help each other and coordinate with each other. Actually, several students can work together in front of one computer screen and then use Abacus together. So all these things can figure out. It works very well previously. And all the students get a very high score in the project. So make sure that all of you, I believe you guys can do the similar way, okay? Make sure that use those projects as the opportunity for you to practice software, and make sure you can use software to solve complicated problems that cannot be solved by hands, okay? So that'll be great experience. Okay, and we also have two invited guest lecture. So last lecture by Dr. Philip Fong was great, and we learned a lot about the different skill devices, coupled mechanics, electronics, those important systems. So next two lecture will be Wednesday, from Professor Jenny Spence from chemical engineering, okay? And then next week from Professor Douglas Spiro from the mechanical and aerospace engineering to give the talk on their cutting edge research. So this will be great. For Professor Sampas, we will listen to her talk on the Zoom, not in the classroom. You don't need to come to the classroom, just watch on the Zoom. For Professor Douglas Spiro, we will go in person. We will be in the classroom, same classroom, okay? So we will be there and enjoy those talks. Very good, very good. That's all the logistics. I hope to keep all of you on the same page. Yeah, is there any questions? And also, here is our schedule for the October, the time, okay? So the tentative schedule. But during the class, I hope all of you participate to ask questions, and we have more discussions, more troubleshooting of the concepts discussions, so that all of you can learn things better rather than just listen to me. It will be great. We have discussions there. Okay. So if our class schedule get delayed due to our discussions, that's fine. We can always run faster at some point to catch it up. Okay. Don't worry about it. Yeah. Okay. So I saw the question from EML. The Abacus project is a group project, right? Not necessary group project. You can form a group to do the project, and also you can do it by yourself individually. Depends on your preference. We don't have any strict requirement. Okay, Amor, you hear me?
Yeah, thank you.
Excellent question. Morgan, does this mean that exam 2 test the matrix and directly? No, Morgan, very good question. So exam number 2 will only cover the material we covered after exam number 1. Okay, so new material, new question, new knowledge. Okay, Morgan, you hear me? Excellent. Those clarify many things. Very good question. Very good. Yeah, I urge you, all of you, ask me question. And because I have two screens here, computer screens, sometimes I will keep monitor the chat. So sometimes if I miss anything in the chat, you just shout out, and then I will answer you immediately. Okay? Yeah. But when you come to the class, mute yourself so that you don't disturb other students. Okay? Okay, very good. And also I received many constructive comments, feedback from you. So almost all of them actually saying that the class so far goes very well, and you guys are learning interesting things, important things. I'm very glad to hear that. So I hope you keep sending me the feedback. Then we can avoid any confusion, avoid any mistakes, and all of you can make sure to enjoy the learning experience in our class in this semester. Okay, so keep sending me that. Yeah. Very good, very good. And my email address is listed here. So just send to me. Don't need to follow. You don't have to follow this format. If you have any new comments, new idea, feel free to email. Don't be shy. Okay. Very good. Okay. So now we can start talk about today's material. Okay. Yeah. So this is the materials in our body. I mentioned it in the previous class, right? So the material is not in the biosystem. It's not just the non-living, not reactive material. They actually can instruct cells. Like here I showed before, the cancer cell can respond to the material, right? So okay, so in this class we mainly talk about the non-living material for now, but FEM can absolutely be applied to living material as well. Okay, so let's go through briefly what we discussed in last lecture, the bar element, and then we will move into the new material, new things. Okay, so what is uniaxial bar? So uniaxial bar is actually a slender, meaning very thin, two-force member. So this element is very thin. The length of it is much larger, usually 10 times larger than the cross-section dimension, means diameter. Okay, so usually very, very thin. It's like a chopstick, right? Chopstick. And then the force is applied to the two ends of the bar. It's not in the middle. It's not in the middle, always in the end. And then the cross-section area of the bar can vary. It can be changing the cross-section area. So that's the difference, right? That's the difference from the spring element we mentioned before, right? Here you can change the cross-section area, and you can also change Young's modulus. So the material property can also change. So that's actually means that this material at a different point, you can actually consider it different. You have to deal with it separately, okay, specifically. Yeah. And when the force is applied on this bar element, there are two types of force. One is the concentrated force, one is distributed force. So here you see two examples. These two examples is called statically indeterminate system and statically determinate system. So statically indeterminate system means the system, you have the force applied, but only by using the force equilibrium condition, you cannot find out the deformation, complete deformation picture of this system. You have to use additional equation, additional relationship, get additional equation, and then completely solve the mechanical states of the system. For the statically determined system, you don't need that. You just need a mechanical force equilibrium. Then you can determine the system. We will talk more details of these two systems. But here you can see in the top system. Do you guys see my screen and moving mouse? Yeah, very good. Because I'm going to point out the things for you here, okay? And also, if necessary, I will draw it, use the pen on the screen, okay? So make sure that you see it. If you have a computer has some issue, you don't see it, let me know, and I can refresh the screen, okay? So in this system, you see, it has a concentrated force, capital F, applied on this point, which is the middle point of this tapered element, right? Number 3, tapered element. And you also have the distributed force, Px, applied on the number 2 element, right? Number 2, that it has uniform cross-section area. So those distributed force actually is not a very unusual. In the nature, it's very usual. For example, if you have a magnetic force applied to the element, or electric force, electric field applied to the element, or you have a gravity applied, those force actually are distributed force on different points throughout across the whole volume, right? And then in this case, the bar element allows that. It's fine. Once they have this kind of a situation, they can deal with it. So they can calculate those force and then redistribute, concentrate them, redistribute into the concentrated force, and then concentrate them to the end node. Is possible. It can be done. Okay. So this is the new thing. that's the advanced point compared to the spring, right? Because in the nature we do have those distributed force, and then this bar element can accept those distributed force. Then it actually can mimic the real situation even better. So this is very good. So there are two types of force can be applied. And also there are two types of system, as I just described, indeterminate and determinate system, okay? And in the finite element, especially for the indeterminate system, this system always existing in the engineering problem. And when this system happens there, people usually solve it by using the material deformation, okay? And then get an additional equation to solve the system. Usually people have to do that. But in the finite element, because of the nature that we solve the problem, which is we discretize the system into small pieces. And then each piece we use constitutive relationship, the Hooke's law, to write the matrix that connects the material deformation, the displacement, with the force applied to the node, which is the external loading. Because we use this way in the finite element to solve the problem, then in fact there is no need to have a special treatment for those statically indeterminate system. We don't need to additionally solve the material property, material deformation in the context of external force, and then to solve the problem. We don't need. We just need to follow finite element method step by step to solve it. And then we can do that. We can solve that. In other words, in finite element, statically indeterminate system and determinate system can be solved in the same way. We don't need to care about it. But we need to know which one is indeterminate, which one is determinate. And then we just use the same method we used before. We can still get the correct results. Okay, that's one strength of a finite element. That's good thing. Okay, and then let's see more detailed definition, very important definition of unit axial bar problem. So to solve the unit axial bar problem, here is one example, right? So this is a bar with the cross-section area, in the squared shape. It has the length L. It has the original length L, original area, cross-section area A, and two force F1, F2 applied to the end, right? And then they get deformed, okay? So if we want to solve those problems, firstly, we would discretize the bar into a number of elements. We can discretize it, okay? We will discuss about how to determine the element size in the next few slides. But the point is, when you discretize the element, you have to have a reason. It will enhance the precision of the final results, or it will enhance the measurement, the determination of those force states more precisely. Okay, those kind of reason has to be there. Then we discretize it, and then it is when we discretize, actually we will make sure each element has a constant axial rigidity. Each element has a constant axial rigidity, EA. EA is axial rigidity. E is Young's modulus. A is cross-section area. Okay. Throughout is length. It is assumed. So that means if the material has different cross-section area at a different point, you actually tend to discretize it to make it small pieces. And in each piece, the axial rigidity is constant. Okay. So that enhances the establishment of the rigidity matrix. Otherwise, rigidity matrix will be very complicated. Okay. So an element, different elements are connected at the nodes. This is the same as the spring constant, spring system. Okay. So they are all connected at the nodes. And more than one element can share a node. That's also, we already know in the spring cases. one node can have different springs or different bars to connect with it. Okay, and there will be nodes at the points where a bar is supported. Okay, that means at the boundary condition on the wall. Okay, and the force is applied only at the nodes. Do you guys hear me? Yeah, excellent. Force is only applied on the nodes. So this is the same as a spring. Force cannot be applied on the edge, cannot be applied on the middle of the bar. That's not allowed. Only applied at the node. Okay. And the distributed force, for the distributed force, like the gravity, magnetic force, electrical force, those force must be converted to the equivalent node force. By the way, if you study physics, you will know actually distributed force is everywhere because we have the gravity everywhere, right? So what we are talking about here, distributed force is more concentrated on the external applied, human applied distributed force. Okay, and then like you apply pressure there. Okay, then those force is larger than just the gravity. Okay, so when we deal with this, we will convert those distributed force into the concentrated force, and then put that on the node. Okay, if the displacement at the node is specified, then the reaction is unknown. Okay, so for example, on the wall, displacement is 0. Then the reaction force on the node of the bar is unknown. If the force on the node is specified, so you know what force is applied on the node, then the displacement is unknown. That is the to be determined displacement. We have solved many problems in the spring system previously, right? So these principles are applicable throughout whole class. No matter what element you are talking about, those principles will apply so that you can construct reasonable matrix equations and then solve them correctly. Okay, and the object of our analysis, finite element analysis, is to determine the unknown displacement, unknown degree of freedom. Degree of freedom is the displacement, uj, right? ui, right? And then we will determine axial force resultant in each element. Those axial force actually can be determined by obtaining the force on the node. Okay, and then you can determine the axial force, and then from there you actually can know what's the deformation of the bar, right? And also you can determine the reaction force from the boundary condition that give the determined or specified displacement, such as on the wall, right? And then once you know the displacement, the degree of freedom, knows the internal force, resultant force in the bar, which is always in the axial direction, means always around the bar. Okay, because there is no torsion, no vertical force for this element. And then you will know the axial force. And then you for the whole system, you determine the supporting force. Okay, then you actually know everything about the system. Okay, quantitatively, this means that for this element, bar element, we have two nodes, and we assume in all the positive direction, like a positive x, like this is all 1D system. In the x direction, we have positive displacement in the positive x direction. Okay, and then they only have a constant cross-section area for this case. Okay, and then here they have the node I and the node J, two nodes. And then on the node I, you have UI, node J, you have UJ. That's the displacement. Between the net change of displacement is deformation of this bar. And then the force applied to this node I is FIE, because this element E, right? Force applied to the J is FJE, right? Make sure you have the parentheses to cover to E, right? And then the material behavior is EA divided by L. We already derived it in the last class. That's the K. That is the spring constant of this bar, right? We derived this last time. If you don't understand that, you can go back to check. And then within this element, force is in equilibrium. So that means all the force applied to this element, they add together equal to 0. So that's the free body diagram. That's to equilibrium, to make sure this element is in static condition. Okay. Of course, when the element has the constant speed move, this principle also applies, right? But we don't consider it in this in our class, we consider static conditions. The elements are in static, speed equal to 0, okay? Acceleration equal to 0. So in this case, force is in equilibrium, okay? And then we can write the force displacement reaction in each node, following the same way we did before. If we look at the Fj, we look at the Fj, use Fj as the reference. Then Fj equal to spring constant times the net deformation with respect to Fj in this element. Then actually is you stand on top of Fj. That Fj minus let Uj displacement J minus displacement I on the node I. Okay, you get that. And then Fi, which is the minus Fj, right? So Fi is standing on top of I as the point, and then it actually equal to Ui minus Uj. Okay, we have derived this equation previously in the spring case multiple times, so this should be straightforward to you. Only thing different is here is not a spring. Okay, now this material has new capabilities. Okay, so in this case, of course the Uj minus Ui is the net change elongation. Okay, elongation of this bar, and then similarly AE divided by L, that's the spring constant of this bar element. Okay, now these are all straightforward, but you make sure you understand, you can derive it by yourself. Then it will become very solid in your brain. Okay. Now we assemble them together. To get the force vector, stiffness matrix, displacement or degree of freedom vectors, and then assemble them together. We have F vector, right? Bold format. F, K, Q, all in bold, means they are not a scalar. They are vectors and matrix. And then E in the parentheses, that means we are dealing with the element E only here, right? So either force or displacement, but not both, as we discussed, not both, should be given at each node. So on each node, you have one information, but not two, okay? And you cannot have zero information, okay? So for example, if we have a displacement Ui equal to 0, we have displacement Ui equal to 0, means that at the boundary condition, then we don't know Fi, in that point. That's a reaction force. We need to figure that out. And then on the node J, we have a force applied 100 Newton, but we don't know what's the displacement on the node J. Okay, so if Fi and Fj, what happens if they are given? If they will fix that point, and then when you solve the equation, you may get wrong. You will get a wrong data sometimes. But if even it's not wrong data, if they are given, then that equation in that row actually is already solved. Then you don't get a new information. So the question is already solved. They don't provide a new help to help you solve the whole system. Okay, so that's the reason. And then on the node, if on the node we have an external force applied, then that force will be in equilibrium with the F force, this small F force we talked about there, because then it will change the direction of both force so that they become an external force to be in equilibrium with the new external force, capital Fi, right? So we have Fi minus Fi F and minus Fi E plus 1. What does this mean? This means it's on the node I, you have two bar connected. One bar is E, another bar is E plus I, another new bar, and then they connected on the one node together. Okay, like here you see this node. Here you have one node. One bar is here, one bar is here, another bar is here. They both apply force to this node, and then on top of that, the bar is also experiencing an additional force, capital Fi. Okay, so then these three forces are in equilibrium, make this node in static condition, and they satisfy this equation, force equilibrium equation here. Okay, then by finding out the internal those force, you can find out the external force, what's the value, or vice versa. If you know the external force, then you get an additional equation that links the force applied by both elements on the node, okay, which is these two forces, okay. So in general, you can have many of springs connected to one node, and then all of them, the force added together equals to the external force applied through non-bar, okay? Just apply direct force, it's capital force, okay? And then, so those are all consistent from the with what we discussed in the spring system. Now, after that, we will have all the bar equation, all the bar written into the individual matrix equation. And then we will assemble them together, okay? As in a system, we assemble them together. It will be in a similar way as we assemble the spring element, okay? Then we will replace, when you assemble these two together, you don't have external force, right? You only have the internal force. So because you are using this equation, you're using this equation. So this only consider internal force, which is this one, those small f here. And then you add them together. When you add them together, you can start to use this force equilibrium equation. And then you replace all those internal force with the external, this big capital F force, right? So then the equation, combine the equation. Here, K obtains, you contain the system equation. So Ks is the structural stiffness matrix, right? The big one, all the bar element combined together. Qs is the vector of node displacement, node degree of freedom, all of them. And you understand that when you add it together, node displacement will not add. They're shared by all the elements, right? And node force will add together. So you have many small f added together. And then small f, based on that force equilibrium, they equal to the capital F. So then we replace with the capital F. That is the external force applied. So this is the vector of external applied force not through the bar, through the direct application, okay? Then you have this equation. They have this equation set. And then here, Ks, this structure stiffening matrix, has the property called it's square, symmetric, positive semi-definite, singular, non-negative diagonal terms. So this actually is the consistent with the spring case we discussed earlier, okay? So that's the property of the Ks. Now, once we have the Ks, we can start to add in the boundary condition now. Using the same way we did it for the spring system, we can remove rigid body motion by fix the degree of freedom, no rigid body motion, and then strike the rules and the corresponding columns out, right? We can strike them out. So then all the unknown will be on one side of the equation, okay? So we will have a new many rows and columns are removed. We have K, Q equal to F. Now this K actually is called global stiffening matrix. We asked about the definition of those different matrix in the exam number 1, right? So this one is the global stiffening matrix. And then Q is the vector of unknown degree of freedom, because we move all the no information, we removed all the no degree of freedom, right? And then the F is the vector of no applied force. So in this case, all the no information are on the right-hand side, all the unknown in the left-hand side. And then we have K here. And this K, actually here, this K is a square, symmetric, positive, definite, non-singular, invertible, because we remove the manual row and columns there. Now this one is invertible. Then it's good. Invertible. Then we can multiply the invert of it to both sides. Then cancel the left-hand side. And then left-hand side only have the displacement equals to the inverse of K times the external force F vector. Then it will calculate directly and the Q, the displacement. That is a unique solution. So then we get a unique Q, okay? Once we get a Q, then we can put it back and then calculate the unknown force on the right-hand side. Then we know everything. And then from the Q, we know the displacement. Once we know, when we use this displacement, we can put it into the original, the element equation, each element, okay? And then we can solve the node displacement, there, okay? And then we can also calculate element force, okay? Because we already know the force external capital F, those values, and then we also know the displacement there. So then we can calculate the internal resulting axial force around the bar element. Okay, and of course from there we already know what's the reaction force. Okay, we know the reaction force, so that the whole system will be solved. You know the internal force, internal displacement, internal elongation of each bar. You know the external force, you know the external reaction force on the system. So the whole thing on the system are resolved. Okay, so that's actually the beauty. The same is same logic. So this is the beauty to solve the bar systems. Okay. Let's to understand those better, we can look into one example together. So here's one example. So this is a bar system, 3 bar element. Okay, we have 3 bar, element 1, element 2, element 3, and then they are connected with one node. And the node, see this node actually is a block has 2 wheels installed at both ends, and then the wheels are in contact with the horizontal walls. Okay, so this actually is a unique structure in engineering. Okay, very unique. So this what it means is that this element, this white color element. Do you guys see my mouse? See my cursor? Yes. Okay. Very good. Very good. So this actually means this object can move around the horizontal direction, but it cannot move in the vertical direction, because the vertical path is blocked by the rigid wall. But when it moves horizontally, it can move. It has 2 wheels there, and also it implies, because it has wheel, so it has minimal friction. There are no friction. When it moves, there's no external force due to friction force. Okay, know these things. It's very, very smooth, frictionless. Okay, so you can see here we have for how many nodes? We actually have 4 nodes. One is here at the left hand side of the element 1. You see one external force also applied to this node. The node number 1. Here is node number 2. Node number 2 actually contains the another end of these 3 elements. So they are connected together in one point. So that point is called node. Here, don't get it confused. It's only one node. And then third node, and only one force will be one force, external force, if they are. Okay. Here we don't have, because all the force internally from the 3 elements are cancelled each other in equilibrium in this node. And the force from the top and bottom walls, they are zero. They are frictionless. Okay. So only 3 force from 3 elements. Node number 3 is the element 2's another end that is bounded on the wall. Node number 4 is the same for the element number 3. You may wonder whether the force on these 2 nodes are the same or not, because they look at element 2 and element 3, they're experiencing some kind of external force, right? Stretched or pushed by the element number 1. In fact, they are not the same. So these 2 forces can be different. The difference can come in from the material property is different. Some material is rigid, some material is softer. In that case, rigid material sustain more force, okay, because they are more capable. Soft material sustain less force, because here you want to keep the deformation of these 2 the same. So if the same deformation, then this one has less force, soft one. The hard one have more force, right? So that's the reason. So don't assume that the deformation, the geometry or deformation is the same, then the force is the same. It's not always the same. Okay? We need to specifically solve the problem to find out. So so when you solve this problem, you start to draw the force, draw the free body diagram. So here is what it is. You have this is the free body diagram. You have F1, F2 on this node, okay, and also U2. F1 also have U1. On the 3 and 4, you have a force F3, force F4, and then displacement U3 and U4. Okay, so these things, this is the complete diagram showing showing this system, bar system. Okay, now, of course, at the node 2, we have at node 2, we have F2 equal to F2, all the internal force from the element, right? Element 1, element 2, element 3, and all apply to the node 2 to have this, right? Now, in this case, you see F2 equal to no F2, right? In this case, F2 equal to 0. But F1 have force, okay? F3, node 3, node 4 have force. So make sure don't mix those numbers. You need to write very carefully. Element number, element notation, node notation, force notation, displacement notation. Everything should be very clear there, okay? In this case, we can, for the element number 1, we can start write their individual equation set, right? So this is the super straightforward now for you. And F2, you can write a similar way. Don't mix those notation, those subscripts. And then for the element 3, you can also write corresponding equations. So all of them follow the same format, but they will change different notations there, okay? And then we can assemble them together. So we have for 4 nodes. Then we will assemble 4x1 vector, 4x4 matrix, 4x1 vectors. And then we start to prepare the global matrix equation. So we always have for stiffness matrix times the stiffness vectors equal to a force. So no matter this force vector is written in the left-hand side or at the right-hand side, doesn't matter. You will know this is a force, okay? And then we have we can start to put in the different components in. So we first put the element 1 in. So you have a K1, because it has node 1 and 2, right? So it will be in the position 1 and 2, both the column and the row, so that they are corresponding to the node 1, node 2, U1, U2, right? And then we have element 2. If you just put element 2 in, then element 2, which is this guy, is node number 2, node number 3. So it's in the position 2, position 3, row 2, row 3, column 2, column 3. So you have this K added in, and then don't change the displacement here. Only put the force here. Only put the force number on the force column. And then element number, these 2, you can actually combine them together, right? So you can have a K1, K2, they are combined together, okay? Don't change the U is the same. And change the force can be added, okay? And then element 3, because here you have a node number 2, node number 4, right? Then it should belong to row 2, row 4, column 2, column 4, right? So then it can be added together. So number 3, number 1, number 2 added together. Then we can combine together, have all the force added together, all the stiffness matrix added together. Displacement remain the same. And then using the force equivalent equation, we can convert all those small force equivalently into the external force applied to the system, F1 up to F4, right? Now, this one is we call a structure stiffness matrix, right? Structure stiffness matrix. And then we can start to strike out some columns and then get a global stiffness matrix and a global matrix, equation matrix, okay? So for specific question, if we have those material of the bar given and the external force actually F1, capital F1 given, then we can start to put a number in now. So here is the stiffness of each one. So here this stiffness actually includes the dimension, length, a cross-section area, and the material properties. They're all included. Then you start to add them together, okay? And then here the node in this question, you can see the node is F1. We already know this is a 40. Here is a typo. It's a 40 Newton. And then F2 should be 0, okay? F3 unknown, right? F3 is on the wall, unknown. F4 unknown. So then in the fourth column, you have 40, 0, F3, F4. And then on the matrix, we are adding different individual 2x2 matrix together. Then we get this equation, okay? And then for the displacement, the U1, U2 are unknown. Node 1, node 2, we don't know. But the U3, U4, they are on the wall. So we know their displacement is 0. They're all 0. Okay. So this is the beautiful matrix. And then we can start to strike out some columns, as we mentioned before, leave all the unknown in one side. So now you leave all the unknown displacement in one side. So you strike out these 2 rows, and then corresponding, we can strike out these 2 columns. Then multiply together, we will have those equations, these 4 equations. Okay. In fact, here we rule out the F. So we have 2 unknowns. So you have a 2 by 2 matrix times a 2 by 1 vector equals to 2 by 1 vector. Then you can quickly solve U1, U2. Okay. And sometimes people actually add this back in. So then F, the 2 unknown F should also be there. Then we have 4 unknowns, and the 4 equations. Here we have 4 equations, right? This matrix is the 4 by 2, right? Each row is 1 equation. Now, yeah, we can start to move that, follow the same way. So then you have displacement solved. U1 is 1.2 centimeter, U2 is 0.4. You can do it by yourself, calculate it by yourself, see whether it's correct or not. Okay, and then we add it back to the force. Then we get the force value. Okay, so this is a very basic fundamental solution. And then you can put the value back into individual, recover that, and then you can solve individual displacement. Okay, you can get an element force as well, element force. So for the number 1, you see it's 40 Newton. Number 2 is 12 Newton. Number 3 is 28 Newton. Okay, so that's what I'm saying here. You see that in these 2 different ones, force are different. Force are different in 2 different nodes, because that is although they experience in same displacement, but the material properties are different. Okay? And here, make sure you keep in mind the notation. Subscript is the node. Upscript is the element. An element use the parentheses to cover it, to make sure this is the element. Okay? Then you won't make a mistake. You will do really well in the exam and in the quiz. Another example here, is we have statically indeterminate bar. So we have this guy have 2 bars. One is narrower, one is wider, and they have different lengths. They are all clamped between 2 walls. Okay. In this case, we can actually cut or discretize this bar into 2 pieces. And you see in the middle, there's a force applied. So that means this element has 3 force applied. Okay. And this actually is an indeterminate system. If you just use the force equilibrium, you actually cannot solve it, because you have more unknowns. If you use the force equilibrium, you have more unknowns than the number of equations. Okay, so you cannot do that. You need to find an additional equation. In the finite element, we don't need to do that. Okay, so in this case, let's use the same way we just described to go through this problem. Let's see whether we can get the final results or not. So in this case, we know the Young's modulus, force applied is F, the cross-section area for 2 bars individually, and then we can start to write the equation for each one. For the element number 1, you have the EA divided by L, right? EA divided by L. E is this, 10 to 11, 10 to 11. So because 100 gigapascal, giga is 10 to 9. So 2 plus 9, 11, 10 to 11 Pascal. So when you solve this problem, make sure convert all the unit to the standard unit. So this E, A is meter square, 10 to minus 4, and then divide by L, right? 0.25 meters. So meter, Newton, Pascal, those are all standard values. So convert all of them to standard unit, okay? And then you have this times this matrix, you have this one, okay? Here, U1, U2 means this is U1 position, U2 position, but there are no real displacement in this expression yet. And then K2, we also can do the same thing. E times L divided by L, right? Times A divided by L, right? And then times this, then you can have this U2, U3, because here we have the node 1, node 2, and node 3. Okay, so different elements have different nodes. Then we assemble this together. So we have 3 displacements, 2 on node force, both are on the wall. Okay, and then the structure matrix. Then we can strike them out, and then we get one equation. Okay, so from this equation we have displacement. We can get a U2. So this displacement at this point is no. So, okay, that's great because other displacement equal to 0. So once we get this, we actually solve everything. And then you can put this displacement U2 into a bar 1. U2 minus U1, which is 0, equals net change. And then times the Young's modulus equal to force in the bar 1. Same thing for the bar 2. We get the displacement, get the force. Okay. Then from this reaction force, you can divide them by the cross-section area. Then we will know the stress there. Okay. So that's how you solve the problem. And this solve a statically indeterminate problem. Okay. So in the finite element, you don't need a special treatment. You don't need to strike out the material constitutive relation. No need. You already implied that. You already implied that in those individual matrix, and then you actually implement that throughout the process. Okay, good. I also provide an example here. You can do it. Answer should be in the textbook, so you can use this to practice. Then next section, we will start to talk about the truss element. That's a very interesting one. So that will combine different bar elements together in the 2D and in the 3D, and then we can analyze them together. Okay. So Wednesday we will have an invited lecture. Friday I think is the holiday, so we will meet next Monday then. Yeah. Let's see. Yeah. Friday is the homecoming, so we will meet Monday then. Yeah. Very good. Very good. Thank you guys. See you guys then. Very good.
Hello, Dr. Tao.
Yes, yes, please. Yes, please. Go ahead.
Okay.